Okay. Good afternoon, folks. Thanks for joining. We would like to share with you some work that we've been doing around deployment and management for the edge. So first off, some introductions. I'm Brent Rousel. I'm the principal technologist for Wind River's Titanium Cloud product.
And Greg Waynes, I'm also an architect on the Titanium Cloud product and done some contributions into OpenStack, Vitrage, and Mazikari over the last few years. Okay,
so before we dive into the edge topic, just a little bit about Wind River for folks that aren't familiar with us. So our roots are in embedded systems, but we also have a cloud offering, our Titanium Cloud product, as well as in the IoT space. So our software currently runs in over 2 billion devices, providing critical infrastructure. And in fact, we have software that runs even off the planet. We have software that runs in the Mars rover. Wind River's Titanium Cloud. So this is a fully integrated turnkey OpenStack deployment, which reduces time to market for operators. Key focus areas for us are around latency, high availability, resiliency, performance, and security. And these are all things that are critical to edge use cases and deployments. Initially, we were targeting the telco space, but there's also been many opportunities in other market segments such as energy, smart buildings, and manufacturing. As well, I also like to point out that our platform is OPNFE certified. So as many of you have probably heard this week, the StarlingX project was launched. So this is a new project that's going to be hosted by the OpenStack Foundation, and it's going to be seeded with the code from Wind River's Titanium Cloud portfolio. And as I mentioned earlier, this is going to provide key differentiators for high availability, quality of service, performance and low latency that's needed for the edge use cases. StarlingX is going to be closely aligned with the OpenStack Foundation Edge Working Group as well as the Akraino Edge Stack project. Okay, I'm sure all you folks have been to many edge computing presentations already, so I won't go into what the edge is. Just like to point out that we've been very active in this area. We've been contributing since the inception, the Open Dev Conference last year in San Francisco, Dublin PTG, and as well as contributing to the mailing list. Okay, so we started an incubation project. We call it the distributed cloud, and of course this would be part of the StarlingX project as well now. So some of the key objectives that we had that we set forward with this project. So we want centralized management across edge clouds. Zero-touch provisioning, so a focus on simplifying the deployment of edge sites. Single pane of glass for day-to-day operator management of edge clouds. Also recognizing the fact that need to scale to a very large number of edge clouds. And that the edge clouds themselves will have very different characteristics. So it needs to scale from a single node all the way up to 100 nodes. And lastly, autonomy of the edge. So if communication is lost to the centralized management, then the edge cloud still needs to be able to keep performing its mission critical operations. And with that, I'm going to turn it over to Greg, and he's going to deep dive more on the implementation.
Okay, great. Yeah, so I got some more detailed information on distributed cloud and a few little embedded demos of the results of our incubation project. So the distributed cloud solution, it's based on OpenStack regions. There's a centralized region, we call it the system controller region, and then there's multiple other secondary regions, which are the remote edge subcloud regions. In the central system controller region, like all multi-region solutions, there's shared services there that are shared with the other regions, like Keystone, and then I'll go into some of the further ones there. But the key capability in the system controller is really we've implemented these system-wide infrastructure orchestration functions. These support deployment and management of the subclouds. They also provide a configuration portal for being able to synchronize shared configuration and configured OpenStack resources across all the subclouds. Provides fault aggregation across the subclouds, as well as synchronizing software updates or patches in an automated fashion across all the subclouds. The remote edge subcloud regions, they're geographically dispersed subclouds or regions. They're connected over layer 3 networks, and basically all of the inter-region communications between the regions is strictly REST API over layer 3. So there's no RabbitMQ or RCP calls going into region. It's strictly layer 3. And then finally, on the edge subclouds, they're running typically or potentially a reduced control plane, just because they're sharing services with in the multi-region environment. And in addition, they may have fewer services just because they're running on a smaller footprint. Architecture diagram for distributed cloud project showing a little more detail. System controllers on the top, the subclouds on the bottom of the slide there, and being Titanium Cloud solutions. The subclouds, just wanted to kind of point out, the subclouds can vary from a single server solution or a dual server solution all the way up to like a full cloud with a controller cluster and a large compute cluster as well. As you can see on the system controller, like I mentioned, there's shared services. There's Horizon, Glance, and Keystone. I'll go into those in a little more detail coming up. There's also a distributed cloud services service that is composed of distributed cloud management of the subclouds themselves on the system controller, some of the fault aggregation, the configuration synchronization across the subclouds, as well as the patch orchestration, and I'll go into more detail on that. And as you can see, of course, there's a Titanium Cloud infrastructure services running on the system controller and the OpenStack services as well. And on the remote subclouds, again, OpenStack services, likely a reduced set of services there due to the sharing. Infrastructure services are on those clouds as well. We show the Cinder backend as optional, although if you're using Cinder, you're likely going to configure it on the remote subclouds just for latency reasons. And yeah, I'll go into more detail on the upcoming slides. Okay, so the Distributed Cloud Manager, this entity provides the REST APIs for basically all the distributed cloud services. And it basically manages the definitions of the subclouds on the system controller. So you can add, delete, modify subclouds. The subcloud definitions contain configuration data, things as simple as name, but also management IP addresses and that sort of definition of the subclouds that the system controller needs. as well as provide status information. The availability is the IP connectivity to the subcloud. It also provides synchronization status for the status of the synchronization of the configured resources for the various areas like Nova or Neutron and that sort of thing, as well as patch synchronization for the software update synchronization. It also provides some administrative commands like manage and unmanage. That indicates whether the subcloud's being synchronized with respect, because you can basically let a subcloud be unmanaged if you don't want to synchronize the data to it. As well as this entity also raises alarms for subclouds. If the subcloud goes offline or is unreachable, it'll raise alarms at the centralized site. And as I mentioned, it's providing the REST API for the other services in the distributed cloud. The shared OpenStack services. So firstly, Keystone in our initial kind of incubation project. We have a centralized Keystone implementation with the edge subcloud region sharing the Keystone, but already in progress and basically virtually done is for capacity reasons as well as for subcloud autonomy, because you want the subclouds to be autonomous if they lose connectivity to the centralized region. We've actually distributed Keystone. So we've distributed the Keystone throughout the subclouds, and then we're using our same OpenStack configuration synchronization engine in order to synchronize, Keystone projects, users, and roles across all the subclouds. Glance is a shared service as well. And again, in our initial implementation, we've provided centralized glance image management, which I kind of refer to it, but it's also really partially distributed. It provides a pull-based model. So we've got the full glance implementation of the centralized. That's where all the images are stored and the repository is. On the subclouds, we're really only running the glance API. It's talking to the glance server on the centralized subcloud or centralized cloud. And whenever an image is pulled, we leverage the caching that's available in the Glance API to actually cache the image locally at the subcloud so that any subsequent references to that image won't incur the latency of pulling down the image from the central spot. So it's really centralized image management, but it's partially distributed with a pull model to bring the images down to the subclouds. Now, future blueprints for that is we're going to actually add an alternative to actually proactively push the Glance images out to the subclouds. So it'll be an option whether you want to use kind of the pull or the push, the proactive push option to push the images out. And finally, Horizon's a shared resource. It's our single pane of glass. Basically, we leverage Horizon and the existing kind of ability to look at a particular region in order to look at the Horizon in the context of a particular region, a particular subcloud, or to look at Horizon at the system controller centralized region, where you get additional panels, and I'll show you this, that provide subcloud overviews. Okay, so a big piece of what we did is the distributed cloud orchestrator. So this provides the synchronization of shared configuration, basically shared OpenStack resources across all of the edge clouds. So you can see at the bottom the type of information it's synchronizing across the subclouds. In Nova, we're synchronizing flavors and extra specs and key pairs, quotas. Neutron, it's security groups, Cinder quotas as well. And then even our Titanium Cloud infrastructure service, we're synchronizing some of the configuration parameters there that make sense that you would want to be consistent across all your edge subclouds. So we basically introduced, you can see on the right, we basically introduced kind of proxy APIs that sit in front of the standard OpenStack APIs and add the semantics of synchronizing that data across all of the subclouds. And that's what the distributed cloud orchestrator does, is it is responsible for pushing that data out to the subclouds. It's got the, all the robustness around, auditing the state of the configuration data that it's pushing out there. If a subcloud's offline when it's initially pushing out, it'll the audit will pick up, pushing out the subcloud information to the edge as well. And then I should mention that as far as quotas go, really the quotas that you configure at the system controller context are really quotas across the entire system. So if a project has a quota of 20 instances, it's 20 instances across the entire system. It's not 20 instances per subcloud. And basically, to do that, there's a bit of dynamic management to the quotas on the individual subclouds.
Yeah, the subcloud is just the terminology we use for an edge.
Okay. Right. Okay. Okay, so the other thing I mentioned that it does is we provide alarm aggregation at the system controller, aggregation across all of the subclouds. So I have a little demo that I'll start here. Okay, so I'm just showing logging into Horizon on the system controller here. You can see that I'm logged in as admin in the system controller region. So I'm, and the system controller, we've added some new Horizon panels for cloud overview. It's got a system controller table, just the one line there. And then it's got a table of all the existing subclouds. And you can see that that table is containing, whether it's managed or unmanaged, some of the availability status, the aggregated alarm status for the clouds. And that, just point out that aggregated alarm status is actually summarized across all the subclouds on the top line of the Horizon, which is visible at all times in Horizon at the system controller. And you can expand the details. Subcloud 1's degraded, so I can expand it. I can see more detailed status information on the subcloud with respect to the synchronization of configuration data for the particular OpenStack services, as well as I can see alarm counts for the subcloud. And then I can also click the alarm and event details, and you'll notice that changed the region that Horizon is displaying. I'm now, if I can point here, I'm now in subcloud 1 region as admin, and now I'm looking at the detailed alarms on that particular subcloud. Oops, I think I'm starting it all over again. Okay. Okay. The next thing to talk about is our patch orchestration. So just terminology. We use the word patch to refer to a software update containing bug fixes and/or security updates. So we, in our existing Titanium Cloud solution prior to Distributed Cloud, we actually support patch orchestration, which is the automated applying of software updates to all of the nodes within a particular cloud. So it automates, walking through all the nodes and updating, applying the patch, applying the software update. Well, basically for a distributed cloud project, we've basically taken it up a level such that we're now automating the application of the software patch across all of the subclouds and recursively all the nodes within each of the individual subclouds. So it kind of walks through the system controller first at the top to make sure the system controller is patch current, and then basically recursively walks through all the subclouds. The software updates or patches can be, are typically non-reboot required. They just require, updating of the software and potentially restarting some processes. But if they do change the kernel, for example, require a reboot, the automation, the patch automation will actually automatically migrate VMs off of the nodes prior to applying the patch. So this is an absolute must. Anybody that's managed a cloud of even 20 nodes, 10 nodes even, it's an absolute must for kind of usability and scalability of being able to maintain your cloud software across clouds. Okay, so I have another little demo of a patch orchestration. Actually, I think I can. Okay, maybe not. Okay, so I'm selecting the, just slow it down here. So I selected the software management tab under the distributed cloud admin accordion menu there. And you can see that I have a patch. The second patch there is an in-service patch for all nodes that I haven't applied yet. So I'm going to apply the patch. And you can see that it's gone to a partial apply state, which really means all I've done is I've updated the patch into the main patch repo, but I haven't installed the patch on any of the clouds or nodes yet. So I go to the patching orchestration tab. I'm going to create a strategy for doing the orchestration. It allows me to select a few parameters, like am I going to apply the patches serially through all of the subclouds, or am I going to do them in parallel? It really depends on how much of your system-wide infrastructure you want going through a patch at the same time. So I'm going to select parallel. I'm going to select two subclouds, and it'll create the patch strategy. And you can see that the patch strategy has, it's going to update the system controller first to make it patch current. Then you can see that stage 2 is going to be subclouds 1 and 4, and stage 3 is 5 and 6. So I'll let it go. Basically going to apply the strategy now. So this is going to, just make sure the system controller has the right patch first. And then it'll start walking through the subclouds. Obviously, I've sped this up so that you guys don't have to watch a progress bar for 10 minutes. Now, so you can see subcloud 1 and 4 getting patched right now. I think subcloud 1 is like 2 controllers and 3 computes or something, so it's going through all those nodes. If I wanted to, I could go right to the subcloud 2 horizon context and actually look at the individual node progress of applying the patch. Now it's on the 3rd phase where it's patching subclouds 5 and 6, basically. And like I said, I sped things up a bit there, but it's done. And like I say, this is, if it runs into any error, it stops and lets the operator address the error. But like I say, it's a must for any reasonable size solution. Okay, the last thing I was going to talk about was our installation mechanism, because this is kind of the day 1 operation type stuff, and this is the idea here is making this as easy and zero touch as possible. So basically, the sequence is at the remote site. You send out the craftsperson. He's going to rack the servers or server. It could be a single server solution. He's going to rack it. He's going to cable it up to Ethernet and the top of rack switch. He's going to cable up BMC access so you can get remote console access. And then he's basically going to do a software install of the Titanium Cloud software. And it's a non-interactive software install. So this guy doesn't have to enter any data or anything like that. He just sticks his USB in, or Pixie boots it off a local Pixie boot server, and then the software is basically running. And the remote guy at the system controller region basically has remote access through the BMC remote console access. So the first thing he'll do is basically run a pre-bootstrap utility, which basically just sets up basic IP network connectivity so we can have some, so we can transfer some files down to the remote server. Then through his GUI, he'll basically, at the system controller, add the definition of the subcloud, configure it with the required information. And then the third step is we'll really generate a bootstrap configuration data. So we'll leverage the GUI to get all the details that are required for bootstrapping the subcloud. And then we'll basically transfer, SCP that down. Now that we got network connectivity, and then we'll run the bootstrap configuration, and again, that will bring up the cloud basically, or bring up the initial server. In the case of a single server, it'll be basically the whole cloud. And then the last step is really to just manage the subcloud. So it initially comes up in an unmanaged state. We'll switch it to managed so that all the shared configuration data that you've configured for your other subclouds get synchronized now to this subcloud. and then basically your subcloud's up and running. So I've got a little demo of that too. Okay, so this is like the remote console effectively that I'm looking at, the local console. The guy is doing the non-interactive software install here. I've obviously sped things up way fast because that booted really fast. Let me just stop it. So it's installed and booted now. The craftsperson is done. Now, conceptually, the remote guy is reaching through on the BMC console to do that pre-bootstrap test. So he runs this little pre-bootstrap script that we have, runs LLDP just to basically sniff, LLDP packets from the attached switch, so he can make sure he enters the right interface for connecting the management IP addresses and that sort of thing. So he enters all that in, and basically now there's IP connectivity to the system controller. So then the system controller guy is gonna, like I said, he's gonna use this GUI to add a subcloud. He's gonna, enter the information, mostly management IP information around the subcloud, and that will add obviously a new line on the subcloud table that has it. We're now doing, we selected a menu item to generate the subcloud configuration file to do the bootstrapping. Again, some more information about some mandatory bootstrap configuration details for the for bootstrapping the cloud. You can see that it dropped a file on my desktop, and basically I got IP connectivity to the desktop now, so I'll SCP that down. And then I'll run basically the bootstrap config here. So that's gonna bring up all the services of the Titanium Cloud. And I zoomed out here basically so you can see, as the bootstrap continues, the cloud will come basically online. And you can see that, it's online. Sync status is not synced because it's not managed yet. On the right, I'm just showing the cloud's up and running. I can run CLI commands. I did a neutron net list there. I did a flavor list there. You notice the flavor list is actually empty. It's not managed yet. So that's what I'm gonna do now, is that I'm gonna manage the cloud. And you can see the sync status go green. And then I'll do the flavor list again, and you can see that all the flavors got synced down there. And then the final step is you can see that the patching is out of sync. So again, I'm gonna go to my patching orchestration, create a strategy. You can see this time it knows that only the new subcloud is not in sync, so it only puts that in the strategy. We apply the strategy, it applies the patches to the subcloud. This subcloud is a single server cloud, so it's quick. There's only one node to patch, and then we basically go back to the cloud overview, and we're basically all green, and my subcloud's up and ready to host services or applications. All right, so summary. So basically, we've shown that this initial work that we've done with the incubation project is syncing OpenStack and infrastructure configuration across all the subclouds, dynamically managing quotas across the subclouds. We've shown the orchestration, automation of patches, aggregation of alarms, a very usable installation sequence for subclouds. This is all stuff that we've got out there, and you're looking for feedback from the community as to, is this the right approach for doing distributed edge management? In progress, I've mentioned that we have the Keystone work to be more scalable and autonomous, and then we've got a bunch of blueprints on the list that we're looking for community help on. I don't know if I'm out of time or. Actually, I can't remember whether this ends at 3:10 or 3:20. I mean, as far as the blueprints that we're looking at, obviously going to continue working on improving the usability of the installation. We got to secure the interregion communications. We don't do that initially. Didn't do that in the incubation work. And then there's some other work around, well, I mentioned the glance work. We're going to make that fully distributed. And then synchronization, configuration. Right now it syncs to everything where we've already got feedback that it needs to be selective. And then there's some much more complicated items like VNF lifecycle management and geo-redundant system controllers that are even tougher blueprints to look at.
Yeah, so these are basically some ideas that we have to move this forward, and we're really looking for input from the community and collaboration from the community to to drive this forward.
All right, so I think we're open for questions.
Quick one. Does the application need to be aware of this cloud, sub-cloud? Or I didn't actually see cloud, so it sounds to me that there is not a hierarchical structure in here. You just got sub-clouds. So does the application need to be aware of the cloud topology or not?
It really shouldn't need to be aware. So basically, the entity that we've put at the top is for infrastructure orchestration. So that should be really transparent to the end application.
Thank you.
Quick question in terms of scalability. Obviously, the point of moving to the edge clouds is we're talking about thousands of nodes. What's the view currently on this project? How can you scale?
Yeah, so the goal initially would be in the hundreds and growing from there.
So today it can only support into hundreds of instances.
Yeah, and as we mentioned, this is an incubation project, and we're looking to grow the capability.
Okay.
So when you were showing the installation and bootstrapping of the various subclouds, is there something in there that actually does any sort of hardware inventory and whatnot, so I can find out, oh, are there GPUs in these? What type of network cards do I have? Or how does that work once it gets this zero touch?
So basically, at the individual cloud level, we have an inventory system that would inventory all the hardware, so it would tell you how many CPUs you have, memory, and then specialized hardware such as GPUs, crypto devices, and obviously things like disks and ports and whatnot.
And is that like an OpenStack ironic type thing, or this is something that?
This is something that, this would be a subsystem that's part of StarlingX.
Part of Starlink, okay,
yeah.
Thank you.
How do you handle fault management and fault detection and recovery?
So those would be handled by components that would run locally on each edge cloud. And so it's part of the StarlingX software base. So we have a subsystem that would monitor the underlying health of the host, connectivity, resource usage, hardware sensors, and things like that.
So do you count on having some sort of agent on the VM?
Well, so at the VM level, we also and this is an optional service. We do intrusive monitoring, provide intrusive monitoring on the VM. So it could do at the simplest level, it could do stuff like heart beating to the VM to make sure it's alive, and beyond that, you can also do invoke application-specific health checks. So Greg, I don't know if you want to maybe expand on that one.
Yeah, like the health checks for the intrusive instance monitoring allow basically the cloud platform to do some intrusive checks on the VM and raise appropriate alarms if there's any failures.
So if you don't have any agent, the only thing you can do is just ping the API. That's all. Just say if it's up or down.
For monitoring the VM itself, or? Yeah, for monitoring the VM. But there's many more alarms that we're detecting and monitoring and detecting to do with infrastructure. as well as the services in OpenStack and that sort of thing.
So I think the gentleman before asked about the application. So how do you communicate the alarms or faults to the application, just in case if they need to do something?
So you mean like host level alarms?
Yeah.
So those would be available through a REST API. So those are all the alarms would be exposed via REST API.
Yeah, the alarms that the Titanium Cloud is monitoring, it can be accessed through REST APIs, and they can also be accessed through SNMP as well. So if an application is interested in getting that information, it's available through either SNMP or REST APIs.
Okay.
But I mean, also, we didn't talk about it because it's not specifically part of distributed cloud, but just part of Titanium Cloud. We do a lot of VM recovery for the VM on their behalf, right? Like if a host has a critical service failure or a critical process failure, we'll actually evacuate the VM automatically for him. It's not required, sort of thing. So we have a Vim process that manages VM recovery in case of faults.
And if a VM goes into a failed state, we'll attempt to recover. If there's a power outage and the rack power cycles, we'll recover the virtual machines as well. So we have a fairly comprehensive list of high availability features for VM management.
Thank you.
Have you any API or CLI in order to create or to enter a new subcloud? Or it's only by Horizon and...
No, it's a CLI as well.
Just specifically, it would be a REST APIs, which would be consumed by Horizon, and as well as a CLI suite as well. Any additional questions?
So when you were talking about the subclouds, I think you made reference to the subcloud potentially being a light version of the control, not having all of the services. Is that just the reduction with the proxies, or?
Yeah, it's one that, I mean, it's using shared services in the multi-region environment, so it wouldn't be, today it's not running Keystone. There's also like things like Cinder are optional. I think we'll make, but in order to be able to run on smaller footprint hardware, we may make other things optional, like telemetry and stuff like that. So.
Okay. So that's one of the things I'm trying to think about once we're getting into, the single node stacks. How light can we make the control? So.
Yeah.
So on our single node stack today, we can basically shrink the OpenStack control plane down to 2 cores.
I have one question. As you're running regions, you don't have the ability to swap workloads from one edge to another edge?
So in the incubation project, that's not something that we've done. It's certainly something that we've talked about, and looking, we would be looking for community collaboration to implement something like that.
Yeah, that was one of the more complex blueprints. The whole VNF lifecycle management across regions is. That's hard.
Okay, thank you.
Out of curiosity, have you considered using Nova cells rather than region?
We did look at Nova cells, but Nova cells is really geared towards addressing the broadcast domain problem within Nova, and it didn't seem to be a good fit for this type of architecture, where we eventually need to support thousands of these things.
Makes sense. Plus, it doesn't satisfy the requirement of having
and Nova cells only addresses Nova as well. It doesn't address any of the other services.
Thank you.
So what kind of assumptions were you making for network connectivity between the subclouds and the central cloud? A simple layer 2 connectivity? Or
Layer 3.
a layer 3 connectivity?
Yeah, so we can support the central entity and the edge clouds being on different subnets. So and both V4 and V6.
Both V4 and V6. So
yeah.
What about reachability aspect? Like, let's say from the subcloud, I mean, you expect each of the subcloud to be completely self-sufficient from a networking standpoint?
Yes.
Okay.
In the incubation project, yes, that's the current state.
Okay.
Okay, I think we're done.
Okay. Thanks, folks, for attending and all the good questions. Thank you very much.